Right, can anyone hear me now? There's a number of issues that would have to be resolved. Matt's just scratched the surface. There's a lot of analysis and merging of types that goes on. All that would have to be revisited, because as soon as you've got a different endianness, all the rules for merging those change. There's the general maintenance cost of who's going to take responsibility for testing this, developing the tests for it, who's going to actually do the validation of all this. Is it going to work on all architectures, just on ARM? If it's just on ARM, then it becomes essentially a large kludge in the back end that has to be maintained. If it's generic, then all the ports have to pay the price of this. All these things would have to be worked out. We'd have to get some degree of acceptance from the community if for anything that was beyond the ARM backend. The ARM backend's already probably the biggest port in the compiler.
So let's not say we'll do it, but if it were to be done, then it would be a cost forever of a team to really support this.
Correct.
You could,
yes.
Nice patches, off you go do something else. No,
not a chance.
Yes.
Okay, it's an overhead.
Yeah.
I thought the premise of this was, sorry. I thought the premise of this argument was you've got existing big-endian software and you want to run it, right? It's for supporting legacy applications, but it sounds like this requires source code changes to go and annotate things, split up structs. Right, so if you have to do that, why not just do the swabs instead of annotating it and then getting the compiler to do it?
Just run the whole thing big-endian. Run a big-endian kernel, run a big-endian user land, just not...
That's the next
the model, I've had my own discussions with these customers as well. The model is potentially, if you're going to, in one compilation unit, if you're going to touch data that is big endian and little endian, you use practice. But the model is if you're in a compilation unit that's only going to deal with big endian data or only going to deal with little endian data.
Sorry, there's no such thing, because you have data on the stack. That's always going to have to be little endian. So in a single compilation unit, if you've got big endian code, you don't suddenly have a big endian stack.
So your stack has to be, your stack will be little endian all the way through. You can't, as you swap between functions, you can't change a function from being little endian to the function it calls being a big endian function, because the stack will have data in the wrong.
So you're only talking about pointers and named variables.
Yes.
Correct. It has to be sort of globals that would be big endian. There's an unresolved issue then about whether locals would be big endian or not.
So
would have to be sorted out.
Because that's what the customers expect.
I think the problem is the customer sees it as a magic bullet.
Oh, I understand.
And it's hash pragma big endian, problem solved, except it's not.
So
we do not have enough visibility of what the Intel solution is to be able to answer the question.
So I was told that there's a white paper describing what they did.
There is a Dobbs article that I have read. It is not sufficient to work out what they do.
By the way, there's also patent application from 2009 by Intel.
I
couldn't possibly comment.
Can't possibly comment on that.
Yeah.
No.
Just about stick your fingers in your ears.
No.
Yeah, let's not go down that route. So you're saying, we don't know enough about the magic bullet.
And the solution that seems, having talked to Rich and others, that we would look at is not the same as, it would not have identical semantics looking at it to what's described in that white paper. And looking at what's described in that white paper, that really is a very, very different kettle of fish to even what I've just described as our way of doing it in GCC, because it's not, you can't do it with the address space mechanism that's already half in GCC.
The other question is, what's the cost of moving all the software to use these packages? Nobody's counting that cost.
Normally you just rebuild everything again.
Right.
Who's asking for half and half?
So
Why?
I think over time, there's a big blob of big endian code, but over time, because of running on little endian architectures, these kinds of customers have typically developed some further libraries and brought in some other applications that are little endian. So you've grown to a mixed endian
they certainly want to coexist with little endian processes. Yeah, that's absolutely. But the statement, the second half of this conversation, this meeting, will be about using the kernel to create bi-endian process spaces. The objection to that was, okay, now I need a complete set of libraries for little endian and a complete set of libraries for big-endian. I like that solution, but that was the objection.
Or just put the whole thing in big-endian, the kernel included.
No, because they don't want that, because they realize they are going to need outside applications that are going to need to be little endian.
So if I have like I said, an application that's been running on the Steven with software for a decade, and I would have all the software expecting a particular engine for any shared data across the processes or applications or the kernel or kernel runs exporting data to spaces or whatever, right? So if I have to go change all that application to do that, that will be a no-starter for any big
If you've got a pile of big endian code they want to migrate away from, but they can't rebuild it easily, well, they're not going to be running on ARM then, are they?
Right.
So I think one of my concerns is that if we go down this route, it's probably going to take 3 years to get a fully working solution,
So
even if we can achieve it.
the bi-endian compiler route.
Yes.
Yeah.
Is there a debugger corollary?
Oh, yes.
The whole toolchain is going to be
The whole
affected,
toolchain.
probably even into relocations and the whole ELF specification.
I think if you don't support big-endianness in a clean way to a lot of these applications, going to a customer, end user, and saying that they have to change their code to support big-endian, they will become a big barrier for ARM's entry into the space. I mean, I'm not saying that it will not happen. I'm just saying that you're going to deal with a serious psychological barrier.
Yeah, I mean,
Understood. I think the issue, though, is that if you do something quick and dirty, you end up with, oh, you can't do this, oh, you can't do this, oh, you can't do this, oh, that was never expected to work. And you just get a raft of bug reports, and the whole user experience deteriorates into a, oh, well, you claimed you could do this. No, we didn't.
well, I mean, I think the best case scenario you're describing, still the output is, if people actually use this, it's a debug nightmare. It's there's lots of it's near far with.
The one thing I can't help but think about this solution is people want to run big-endian software because they don't want to touch that software. They want to take it and just run it because they've validated it or they've certified whatever.
Most often it's probably because the person who wrote it is no longer around. They don't know how it works.
And with this solution, you end up having to touch it. Why not rewriting it in the little Indian way and be done with it?
So you've hit the paradigm, the puzzle, which is in order to implement a solution, they have to touch the code. They really don't want to touch the code. Right. So why would you? Yeah.
So, but my understanding of the other solution is they don't need to touch most of the code. If the core of the thing was running big-endian, they don't touch that. They just set a compiler flag. The periphery of that module that interfaces to other loadable modules, they have to put in pragmas to that, but they don't touch the core. So if that's not the solution we're looking for,
This is not the solution. I think it's
worth So just
there are multiple stacks here, and some of them have moved to Intel and are using a solution like this.
So
other stacks which are running on big-endian systems today, which want to move to ARM, and for them they don't like this because this solution means mucking around with the code. Whereas stacks that are running on Intel,
let's try and
can't we just sort out the tools to do it on ARM?
Yeah.
So both sides want to not touch the code. There are two different classes of stacking.
Let me try and draw this part of the conversation. So it's big, really big.
Yes.
Right?
Really, really big.
Really big. You thought it was a long way to the corner shop, but it's really,
really big.
and you have to touch code and shit. So, and
but there is a solution, or purported solution, to some aspects of this out there. So
Yes.
if we had a bunch of engineers and they had lots of time, you might send them away to write down the solution they could think of, and you could then take that and show that to these people who then go, no, I don't want that.
Yeah.
Whatever, you could go through that, but let's park that, because I think you only go do this if the other possibilities are worse, right? So let's segue into the mix.
So regardless, so even in the second half, there's compiler work to do, right?
Yes. There's a whole bunch of tools work to do the other thing, and we should include that. This is why these to be done. So let's switch end. Let's go to the other side, which is okay.
If I may, one more question for the compiler.
Sure.
Usually we want to the compiler help us to find where the code needs to be modified, but we usually not ask the compiler to modify. Do you understand?
So yes, my understanding is that there's sparse so if you see there's something sparse in the Linux kernel, is there the checker?
Sparse,
and
yeah.
that can pick up endian.
I believe so.
So there are tools, not in the compiler, but the kernel has.
Even that, even using sparse would require some kind of annotation of your source code.
Yeah,
Yes.
you have to use underscore.
You have to
as
touch
well.
the code, right?
Yeah.
Right.
So then you have
Right.
to go touch the code again.
Okay,
And it's only as right as your annotations. So if you're
Yeah.
adding the annotations to check if it was right, it
Yeah.
doesn't really make any
but
sense.
there are tools out there that can help you work through the translation of code from big endian to little endian, step by step. And yeah, so and sparse.
Well, let's cover that in the next bit, because that's all part. Let's have a discussion that says, what does the kernel look like? What's that? You know.
So the kernel.
And then let's think about what all the tools and things that need to
Right.
exist to build that system.
So if you wanted the model you're talking about, where the kernel runs in one endianness and can create applications in another endianness, theoretically, it shouldn't. You basically tell the kernel you can run this type of application, and when we create the application, we basically set the bits that this is a beginning application. But like you said, you now have to have a whole. You basically have to have two user lands on your system, right? So the question I have is, you're talking about running big endian, little endian components at the same time. Is this being done right now in Intel parts? No.
No, they're using the compiler patch.
Okay. Because then their approach would be to run it on separate cores, and to run a big endian core and a little endian core. But this is people actually want a single core running both big endian and little endian.
Running big endian apps on a little endian kernel by writing wrappers around the system cores that share data. And another part, you can get about 70–80% of them for free if you enable the compat layer, even on a 32-bit application. And the compat layer, with the same data structures, it has the advantage that it does get user, put user on each member of a structure. You hack the get user, put user to check the endianness of the current thread, and does the swapping. So you get this conversion for free with some overhead. There are bigger problems like IOCTL calls, so you have to deal with them individually in each device. And the futex is another problem, because there is that's a big system called the futex one, sharing some data, so you have to add a wrapper around that, especially if you're on synchronization between 32 and between a big endian and a little endian application. This may work if you try to keep your like self-contained application. You have one, it doesn't communicate with the other little endian applications in the system, so you may be able to get something here.
Well, you also have things like, well, I guess the system call handling might handle this, SysFS files. If you've got that raw data you're getting out of SysFS.
If they're string-based, then it's all right. I know someone has done some investigation, made some good progress, but it's not the full solution. So
ARM, the voice of ARM needs to be heard.
Okay, so having written some of that compat code, I don't think it's realistic to have the compatibility wrappers for endianness conversion in the kernel. But we do have a set of libraries already, which is part of the QEMU project, which is able to run, to translate system calls from endianness to another endianness, or even from one architecture syscall interface to another's. And something like this has been done before on PowerPC, where we, for an x86 Linux emulator, where you would run a native little endian x86 application on a big endian PowerPC machine.
Yeah, I agree. If you can keep it out of the kernel using QEMU to do this translation, it's even better.
Well, at least look at QEMU as prior art, right? The ioctal problem is one of the things that people always, well, it's intractable problem because you got ioctal and you can't map them all. Well, QEMU user space manages to do pretty nicely with a set of predefined translations for ioctals. Right? It doesn't handle everything, but right, and if you're not trying to port user space drivers, then it's probably good.
But so it strikes me that sort of thing, the way the solution goes there is that we say, okay, here's a framework, and we do the basic work, and if people, members, whoever need to add support for various ioctals, we can tell them how to do that, or do it for them if they're members, and go through that way. It's at least then tractable, that's a bounded, it's this bit.
Solve the problems as you hit it.
You solve the problems as you hit it, it's a bounded problem, it's this library that.
My question in that solution is, do you put the solution in the kernel, or do you put it in, like, the C library?
I think few texts can only work if you put it in the C library, thinking about it. I just don't think you can do IPC, but maybe you don't care about bi-endian IPC.
The C library is a more attractive.
I think you have more semantic information.
Myself.
Yeah.
Yes.
Well, what would happen to that? It would have to be one.
Yeah.
The other way to possibly do it is thinking off my head, so I don't know how realistic this is we could hook into this just as a layer on top of the syscall interface and just say this, because it's the syscall interface, and then few texts may have to be in the main library, but try and do it so that it's one place that we can do under a license such that other platforms, libcs, can pick up the same stuff without much.
A lot of lower class, performance class networking devices don't necessarily use libc.
There's uselibc.
Yeah.
So we'd have to also.
You will be missing out on a class of
Or you end up with a list of libraries that you have to chunks through to ever, as the user.
You can only do it as a translation layer if you understand the data structures, which you can't do with an ioctal.
I think if you're in those lower class of machines where you're saying, oh, I can't afford 4 meg of memory for e.g. libc, then you certainly can't afford a set of libraries for big endian and a set of libraries for little endian. I think you're out of the big endian, the dual endian solution, those small class of products.
In all of this
doing the 2 library stacks as well, that already exists. You need 2 sets of libraries to support these things, big endian and little endian. So that does sound like it could be made to work. I don't know how many libraries are needed. Someone has some idea of what the actual set of software is.
Well, I don't think we know. And you don't know once you actually take the code and try and run it and discover you need another library. That's the way it works.
Do we need
Fancy bootstrapping another file system?
Do we need 2 elf loaders?
Yes. You need to do. Basically it's like the difference between GNU API, GNU Linux API, and GNU Linux API hard float.
I think, the prerequisites for this, imagine you're going to just create a pure big endian ecosystem. You have all those prerequisites, and then you have a few others. Right?
Yeah, that's exactly right. It's a superset of let's run a big engine system, let's run a mix engine system, it's which is where I was kind of going to go actually the next thing. Why don't we just do virtualization?
This application that you're talking about, how many of them need to share data between little endian processes and big endian processes?
So networking dudes, how many of these applications share data between the big endian and little endian?
But I never got a good answer on that. It's much more complicated than we can possibly decide.
The colleague here says not, they're all just big endian.
So why are we talking
Yours are
about
all
this?
just big endian.
Yeah.
FMT system. So why don't you install Zen and have a PV system?
I'm sorry?
Why don't you install Zen and have two virtual machines, one
Well,
for the big
that's
endian world, one
kind
for the
of,
little endian?
that's maybe where we go to. That's
what we have in KVM already.
That's another work that's good. On the bi-endian kernel support option, I don't know if Catalin, do we have a sense of how, relative to the toolchain option, is this the kernel approach a much bigger, much nastier one, or is it more practical?
Well, it would be hard to upstream, that's for sure. Yeah, the kernel option, it would be hard to upstream to get into the mainline kernel. Yeah, and I'm not sure anyone got to the end of having the full implementation done and say, look, it works without any drawbacks. I know for sure that people that tried it couldn't get the Futex fully working. So maybe the QEMU is a better option here, since it does the translation.
I don't know if I understand that. It's sort of, and sorry, I don't really understand cutting that much, but so it means you have some sort of emulation?
QEMU can do user emulation, so not full platform emulation, but user emulation, where you start your user space process with the bin FMT support in Linux, so bin format. It can start QEMU with an argument. It takes the application as an argument, and it does all the system code. So it executes the code, most of the code natively to execute. Yeah, it does code translation, but a lot of stuff, if it is ARM on ARM, it shouldn't do that much just-in-time compilation.
Well, then that would have to be implemented first.
Yeah. So I think any solution that we wouldn't integrate based on so since the instructions are the same on big and little endian B8.
Yeah, but QEMU doesn't.
QEMU
has no framework for doing that. The assumption is if you're running QEMU to do system translation, it's because the architecture is different and therefore you're doing code translation.
So it translates ARM to ARM.
Well,
or big endian ARM to little endian ARM.
Yes, but nobody would do that.
Sorry, I'm supposed to be chairing it. Where we're going, just to where the conversation is going, is we could modify syscalls so that your big endian application gets magical things occur and the kernel just runs. And we sort of started to discuss the idea of actually you do that via launching QEMU. And Peter there says, well, actually, you'd be translating from ARM to ARM. Which is
it's the wrong level. It's,
whatever.
I think it makes much more sense to do it in the kernel, right? It's
yeah, but and Catalin says, don't put that code in the kernel because it just ain't going to go there. What we haven't discussed is what is the cost of this? Where are all the compilers, the libraries? Could you build a big endian ARM system today that would run? Let's forget the big and little endian kernel thing, but can you build a kernel and user space? Does it run? Does debugger work? Does all of that go? I know, but I was thinking about how you build the thing you're going to run with KVM first.
So, on the toolchain side, so I'm not sure. Linaro haven't done any work on the big endian ARch64 compiler. I'm not sure what the state of that is. For ARch32, there are big endian works if you don't use Neon, and if you don't use advanced SIMD, and if you don't want auto-vectorization. There are issues with big endian on ARch32 with auto-vectorization, and they're fairly large to solve, so there'll be some issues there.
There'll be issues on ARch64 in big endian, at least to start with, for Neon. But
Let's leave 64-bit out for the moment. Okay. So yes, need to spend some time fixing up the compiler for AR32 bi-endian for Neon, but if you could get something working today in the compiler, code generation from the compiler, that there's bound to be a few issues because we don't test it frequently, but where I'd be fairly confident that we could get something out bi-endian-ish as long as you don't turn sort of, as long as don't turn Neon on. Stay at ARM v6. Please, pardon?
It's things like the auto-vectorizer.
So you can want to run the auto-vectorizer over the code. So yeah, stick to integer scalar FP.
VFP okay?
Yeah, VFP should be okay. But so moving further out, we've not built or tested bi-endian systems. So there's assembly code in the libraries that in theory should work or should have been written with big and little endian in mind, but I'm sure it hasn't really. So we could go through and we could bootstrap and we could go through and work it all out. It's all a problem that, and as soon as we go bi-endian, we're going to have to do this. It's work that needs to be done to solve the bi-endian problem, whatever solution we come up with.
So if you had some engineers at your beck and call, and you were given the problem of bi-endian, would you say to them, build, here's the kernel, here's the applications, go build things, and start to debug and run it. Tell me what's missing, build it v6, build it to it. That's what you do.
And get it fixed. It's a bootstrap. It's exactly the same as what we've just done for an AR64 bootstrap. Yeah.
And a lot of people are doing exactly this, right? So there are lots of companies who are running bi-endian ARM systems.
Are there? And are they?
But there's the old IXP4XX. So there's Debian support for the old Xscale network appliances. Then there's at least one Linaro member who's running bi-endian SoC with a complete user space stack, and I'm sure they have issues, but they're all solvable, obviously.
So the point that Wookie has just made, in this great sentence, is that that's very old, that's pre-EAVI, that's Xscale, that's pretty old.
That's B32 rather than B8 that we have for March.
C32.
Yeah, so let's.
So nice that they do that, but that's not necessarily
No, but also on Cortex A9, there are SoCs running with this today, and there are other people porting our upstream ports to that.
So that gives us hope that it'll work. Yeah, it's perfectly doable.
But there will be a continuous cost even in the future, making sure.
Yes, but
That's the same as.
it would be lower than the bi-endian solution.
But yeah, but as you update the tools, you're going to just need to test it bi-endian. Yes, that's much lower than the cost of the bi-endian compiler will be. If that's important.
So tentatively, if you can bootstrap this, you can start building things, you know, find problems, there's debugger breaks,
Yeah.
you want it. And then you'd want to run it. And so my tentative direction would be bootstrap and then use KVM. Two systems.
Yes.
It's kind of where...
So when we say KVM, we're talking about a guest OS running a different engine as from a host.
Yeah, two OSs.
Yep.
One running big, one running little.
I don't think that would fly.
That actually runs.
I know functionally.
No, it runs, really. It's not hypothetical.
Yeah, it's...
Sure. The point I'm trying to make is that there will be a few percentage of performance cost, I would
Oh,
assume.
you mean you have virtualization involved, so
Yeah.
yes, your performance.
So that
is lower.
may be a hurdle for some of the networking applications because you're looking at packet processing throughputs where you hardly have a few cycles.
Okay.
of processing.
Mark, just as a question, if there's a cost? What is the cost of virtualization in rough percentage? What would you say it'd be?
It's hard to say. It really depends on the workload. So you have, for example, 2 stages of memory translation. That has a cost. You use more TLBs. You look up more page tables. That has a cost. Injecting interrupts. Interrupts are virtualized as well, so injecting an interrupt takes a longer time. Yeah, there's all kind of smallish issues. That really depends on the workload.
Because all these issues we've got have got, all the solutions we've got, apart from building a complete, just plain big-endian system where all the hardware is big-endian, have a performance cost.
Yeah, you can't have your cake and eat it.
Yeah.
No. So if you want to run big-endian software, you're going to take a performance hit here.
Yeah, if you're running big-endian software on a listed engine system, there will be a performance hit.
No, if you want to run a big-endian software on a system that is essentially little endian,
yeah.
you have to take a hit.
Sure.
You'll try to limit it, but you'll take a hit.
So when you say little endian system, you mean like the kernel and virtualization?
Yeah, you have, at least your hardware is essentially little endian. You have some layer of adaptation, whether it's code generated by the compiler, the syscall's translation solution, or the full virtualization.
So I understand your comment if you're including some of the software layers like an operating system and virtualization, but if you're talking like a vanilla CPU that supports both endianness, I've not seen cases where, at least in this process I'm aware of,
if you have hardware that is essentially big-endian devices, and you run a big-endian kernel, big-endian application on top of that, you should see zero hit. But it's a relative. Then you start by swapping. You can have a performance hit.
Now the real performance hit is not in the translation. It's the performance hit in that solution is just getting packets in and out of the virtual machine. If you do packet processing in a virtual machine, you have a much larger impact than just the endianness conversion.
But if we go back to the bi-endian compiler for a little bit, I think Intel has published a paper and they have published performance numbers as well, right? So on the dual endian compiler or bi-endian compiler, they have very aggressive optimization for removing the swaps that are needed. So they retain the big endian semantic of the program, but make a big endian program work on a little endian system. And the performance overhead that they have published in their articles is not that great. I mean, it would certainly be lower than what KVM would end up incurring. I mean, they say 4 to 5% for running a mass.
I've seen 5 to 10%, so yeah. So for that, the bi-endian compiler, but that's not the only cost of the bi-endian compiler. The bi-endian compiler is a major support cost, major development cost, development cost, support cost, upstreaming cost. Yeah, and you've got to change the source of code.
The source modification percentage is also published in that paper. So it's only.
So the paper that I've seen from Intel doesn't tell you enough to actually know what they're doing.
Yes, but it does insinuate that majority of, so say you have a massive code base which has bugs, which has dependencies on the fact that it depends on the big endian semantic, right? So 95% of that code base is not going to require any code change. It's only the 5% of that code base which interacts with the remainder of the little endian system that needs to have code annotated with pragmas or whatever else. But the whole idea of the bi-endian compiler was to not have to touch massive code bases that have big endian semantic built into them. Right? So Intel, to solve that problem, went the compiler route. I mean, they did implement a whole compiler to solve that problem for their customers. And those customers are in the networking space, obviously.
Yes.
So if ARM needs to play in the same networking space, maybe there are, so those very same customers would be looking at ARM platform, and they have an existing solution with Intel where they didn't have to modify their massive code base. Whereas in our case, we would have to say that run your entire code base in a KVM virtual machine.
same time, actually, at that point, you say, well, actually, you don't have to change your code base. Just run in a virtual machine. Which is the advantage of the KVM code space one, is if, as long as you don't need communication between this engine and big engine processes, you can just run in a virtual machine, and we can look at the hit, and I'm sure there are optimizations that could always be done. Maybe we can't get to the same.
You might actually want. You might actually want to run it the other way around, like have the outer kernel be big endian and the virtual machine be little endian, if you're doing the high performance packet processing in the big endian kernel.
I think the other thing to remember, of course, is that Intel doesn't have the option of a big endian.
Yes,
solution.
I understand. Yes.
And they've been forced down that route.
They can't run the hardware in big endian.
Correct.
Yes.
They didn't publish the cost of maintaining this compiler, did they, in the paper?
No, but I understand that the users of it are paying a lot of money for it to be maintained each year.
Sorry, it's my duty as chair. Just try and bring this back to some point. If we had some engineers and we were going to go do something, what would we go do is the question that I've been asking. And I think the first step of bootstrapping, actually building things, seeing what big endian can, if you can build a big endian process application set and start running it, is a good thing. The solution beyond that, in terms of do you go do compiler work, not sure. I'm sure you can gently look at that and try and understand a bit more. Maybe there's some customer thing the networking dudes can do to find out what that tool is doing and what you might want a compiler to do. So I think it's some research. But if I had engineers, I'd start bootstrapping the big endian thing. And then you can look at, does KVM make sense? Does a QEMU layer make sense? Does ioctl, do these things actually make sense because you have some performance numbers? And it would also help Mark's effort. If in fact it's got something proper running in big endian and virtualized, would be pretty neat testing.
That actually works quite well. Like, to give you an idea of what's been done, it all started when Ben started pushing some patches last month, like the EA supported code. And it all started as a joke. Oh, let's try and roll that to KVM. And it took surprisingly little effort to have something right. Mostly fixes and some support in Vertile to support bytes. We have a fully virtualized OS, Linux kernel, and some user space running.
So a pretty good test would be to run two systems, one big, one little, virtualized, with some sort of workload, and then that. Yes.
It's not well tested. Yeah. So Ben came along with these patches. Yeah, he fixed most of it. We fixed up some more of it, and that's great. Now it'll go quiet for a year, and then someone else will pop up with a whole load of fixes because it will regress. So, whatever you do, you need people maintaining that and testing it because there are no platforms, or very few platforms.
Do you want to grab?
So I think to your action item list, one thing we need to add is possibly with the existing v32 code is doing little endian builds in their Linaro CI loop.
Big
endian, sorry. Yes, big endian builds in the CI loop.
Yep.
So one comment is use a little endian in instruction with the big endian in data. It works for years. We have the application running on for about 3 years.
Okay. So can we boil that down into a set of next steps?
So it sounds like, the first toolchain next step is to test a big endian compiler and and possibly work through to producing big endian binary releases on a glibc based. Let's start with glibc because that's what you've got. Is the next step. And that's actually shouldn't be too much effort to turn on testing and. It's eglibc, yes, but glibc sort of.
glibc and eglibc are merging again then.
Oh, are they? Okay.
Pretty much. They're forever merging and parting. And is there a kernel, some next steps in kernel language?
I think what I said before, the beginning kernel builds in our CI loop, and it sounds like we might be able to test those on the high-bang platform.
In theory, you can use any platform, but I need the BEA or BLU platforms because we need to read the write-out macros which convert to little engine for devices and just work.
So that was the first time.
But well, I think BLU ED. The only thing that I got wrong was the frame buffer.
So I said platform, the real view.
Yeah.
So the new virtual platform would be the ideal target, I think, because it doesn't have any hardware drivers.
Okay. Yeah, except you need to fix Vert.io.
Right, and I said, but that would be a reasonable thing to do.
The fixes to Vert.io are largely in the spec.
As a small upgrade to the spec, and well, that's a small.
But
a tiny rewrite.
But that's what we'd want to do anyway if we were looking at a KVM.
If we're looking at doing that kind of formal things, yes, we have to.
Yeah.
We have to update the spec.
Yeah. Okay. So test the big-endian compiler, do a release based on glibc, whatever. Start big-endian kernel builds. Platform is review EB, and once you've got all of that done, you will spin KVM in there.
Yeah. Well, actually, we don't need the review thingy for KVM, but yeah.
No, that's okay. The next step, once you've built it all and you're good, is
once you have a chain and a library, once you can reach the space.
Built using open embedded. There's already some patches to do big-endian builds. We have a customer doing that.
Okay, that fits nicely with the RT patch then. So open embedded, build it that way up. Is your build target?
Yeah. Well, I think we'll use what we're currently doing, just add a B tag on it.
Yeah, I mean, your binary tool chain, you can cross tool ng, that's fine. But the root file system.
Yeah, that would be.
Cool. Well, let's go do that then. Yes, Mr. Wookie?
Do you have any feedback that actually have this problem to the degree that two separate systems versus one with the intention to share application space versus two
Well,
virtual machines?
feedback.
We have no idea about that, right?
Feedback here was they just want to run big engine. Right.
Okay, that's yeah.
But yeah, I mean, the networking guys can go poll their customers and talk to them. And there's a bunch of crank the handle work that we should go and do. And then these guys can go, does this match my customer expectations? So we should do it anyway because it's useful. But, and then quite what configuration people run these systems in, what makes sense in products, a whole other set of problems.
So, but we have done that polling and they say the compiler solution. So.
Some of them say yes.
The ones that aren't here.
Yeah, but we don't know why.
Yeah, and sometimes one frustration I get sometimes talking to companies is they say, you must do A. And I say, why must we do A? And they say, I don't know, my customer told me to do A. And so we're missing some vital reasoning behind doing A. But anyway, we can do that. So we've got some next steps. It's a good discussion, thank you. Thanks for the voice of ARM. It sort of floats in the ether. And we will discuss this one further.